Hi, my name is Julia Bush, and this is my presentation for Lab 4. So, as an introduction, this lab explores the concept of energy and current conservation in circuits using capacitors, resistors, and batteries. And we explore these concepts by downloading a virtual circuit board through Java to simulate electric circuits and predict, measure, and analyze their currents, and how that changes when you add different components to the circuit. So as some starting measurements, for the first circuit, I predicted that the current for the first ammeter and the second ammeter would both be 0.2 amps. Because of the loop rule, the current should be the same throughout it. And the measurement for the actual circuit reflected this, and it was also 0.02 amps. And after reversing one of the ammeter's direction, the current should read the same value, but it would flow in the opposite direction. So for the voltmeter reading, when I replaced one of the ammeters with the voltmeter, the reading was 0 on the wire, 0 volts, and that's because there's no resistance on the wire. So this is my graph representing the change in volts for each section of the circuit, because you would switch like where the voltmeter reads for each different section. So from A to B, it was 3 volts. And then from B to C, it did not change on the wire. And then from C to D, the voltage decreased by 0.96, and it did not change from D to E and then E to F. It decreased to 0 volts, and it stayed 0 throughout it. And the sum of all of these readings for voltage is 0 because of the loop rule. The potential difference across a circuit, a closed circuit, should be 0. The current throughout this process stayed at 0.02 amps, and it did not change due to the voltmeter because this is a simulation, so the voltmeter did not skew our results. And the current became 0.06 amps if you place a wire parallel to the resistor, and this is because the electrons will choose to go to the ammeter as opposed to the resistor, increasing the current at that location. So here are my calculations for the resistance for each different place at the circuit. So I calculated using the change in potential difference over the current is equal to the resistance. So for the resistance for the 47 ohm resistor, I got 48 ohms, which is pretty close, and my result for the 100 ohm resistor was 102 ohms, which is also pretty accurate. And then the ammeter also had 0, as well as the wire, because they do not have resistance, because they don't have a change in potential difference. So here's my model for the RC circuit, where we added a light bulb and a capacitor. So I observed that the light bulb went out over time when it was charged by both a battery and a capacitor, and this was like an exponential decay, like we saw graphs during lecture of. The current also decreases with time, and this is in a similar way, like it is an exponential decay as it runs out of charge. So the time to charge the battery, or the capacitor with the battery, I observed as 20 seconds for the 10 ohm light bulb and 39.7 seconds for the 20 ohm light bulb. And then the times to discharge were very similar to their times to charge. It was 20 seconds for the 10 ohm light bulb and 39.8 seconds for the 20 ohm bulb. And here's my graph of the potential difference, the natural log of the potential difference versus time. And as a conclusion, this lab was a little different than it would have been if we had been in person, because real ammeters would have been affected by the voltmeters, so the current value would have changed throughout the experiment slightly, but as this was a simulation, we saw that the current just stayed at 0.02 ammeters throughout most of the experiment. Also, if this had been a real hands-on experiment, the capacitor probably would have taken longer to charge than 20 seconds, which is what it should have been ideally, due to external factors that we didn't see with this being an online application. And that's all I have for this week. Thanks for listening.